All right, so this is lesson 4.3. It's called Finding Time. And the gist of it is related to the exponential equations we've been working with. For example, maybe we put $1,000 into an account at an interest rate of 5%. That would give us an equation that looked like 1,000 times 1.05. There's my 5%. And T here would be the number of years. And we've been plugging in the number of years to see what we get in the future. Now, what if I knew what I wanted to have in the future, but I just wanted to figure out how much time I need to make that happen if I have $1,000 to invest? That means I need to find this time up here. And we haven't yet solved an equation where we solved for the exponent. So that's a little bit different. So I'm just going to go to an easier problem than this one here, and we'll come back to that. We know, for example, that 2 to the first power is equal to 2. And leave a little space. 2 to the second power is equal to 4. But what power of 2, the question mark right there, would give us 3, right in between here? How do we find that exponent? And besides guessing, the key to finding an exponent, you use logarithms. So logarithms find exponents. And there's a couple of ways to go about that. I'm going to give another example. We'll come back to that. Think about 10 to the power 1 is 10, and 10 to the power 2 is 100. Suppose we wanted to know what power of 10 would give us some number in between, like maybe 70. So how do we find that power? And again, the key is the idea of a logarithm. If you look up logarithm in the dictionary, what you're going to find is that the logarithm is an exponent that produces a certain result. And our calculators have a logarithm button for bases of 10, right? Notice here, the base of these powers is 10. If the base isn't 10, then we got to be a little bit trickier on our calculator to try and find the power. So that's, I'm going to do the base 10 one first, and I'll come back and do the base 2 one there. So the trick with the logarithm is, again, a logarithm is literally an exponent. They are the same exact thing. So this question mark up here, my missing exponent, is a logarithm. And in math, we abbreviate the word logarithm with just log. Now, my base is 10 here, so we often write a little subscript base right here. And then parentheses comes next, and the target number, that result I want to end up, goes there. Now, base 10 is our number system, right? We have powers of 10, right? Tens, hundreds, thousands, 10,000s, and so on. So because that's so common, because that's our number system is based on 10, we usually abbreviate this right here and just write log 70. So if you see no base, then that must mean base 10. So I'm going to go whip out a couple of different calculators and see what the calculator says about the power I need for 10 to get 70. And I'll use a couple different ones. Desmos, my favorite, scientific. It has, where's its log button? It isn't on this screen, so it must be on the function menu here. And there it is, log. So I click log once I find it on the keyboard. And then I just type the number I want to end up with, which was 70. And this says the power you should use is 1.845, blah, blah, blah. I'm going to test to see how true that is. So that's the power of 10 I need. So I'm going to take 10 and raise it to that power. And I'm just going to type it out. 1.8 gives me close, 63. 4, 69, 5. The more decimal places I add, the closer I'll get. 0, 9, 8, 0, 4, and then all of a sudden it says it's close enough to 70. Now, actually, this number right here on the screen keeps going on and on and on and on and on, but that's okay. We only need a few decimal places of it. In this case, notice I had to add quite a few to get to 70. And when I had less decimal places, I was just close to 70. But it's the logarithm that allows me to find that power. Let's take a look at the notes again. So I'm just going to rewrite this. 10 to what power equals 70 is the same thing as saying what is the power, log means exponent. So this is what is the exponent of 10 to get 70? Right? And the thing here is a logarithm is an exponent. Log is exponent. What was the exponent here? It was the question mark. What's the log equal to here? It's the question mark. Equal is. And we can rewrite that with anything. So earlier I wrote 2 to what power equals 3. So if I wanted to rewrite that as a logarithm, I would write question mark equals log. You got to write the base. In this case, it's 2 of 3. So this says what power of 2 is 3? Question mark. Now the problem with this one is my calculator does not have a log base 2 button. It has a log button and another button called ln, which is like the log. I'm just going to use the log button. So what do you do if it doesn't have your base? Because log on its own just means base 10. Here's what you do. Turns out I can rewrite log base 2 here with the base 10 log by just writing it as log of 3 divided by the log of the old base 2. And that's the trick. So I'm going to test that out and see if it actually gives me a number so that when I use that as the exponent, 2 to that power is 3. All right, so my claim is I can use that log with 3. Now that right there is the power of 10 needed to get to 3. So to adjust for base 2, I divide by log of 2. And I get a different number than I saw before. So this says if you make the power 1.58496-ish to base 2, you should get about 3. So let's test it. 2 raised to the power 1.58, what was next? 584. 96, and the more decimals I add of this number up here, the closer I get to 3. So what would be next? 25, if I didn't want to round down or round up. And look at that, I'm getting closer and closer to 3. And if I keep going, I should get pretty damn close to 3. Not as close as I did last time to 70, but pretty close. So logarithms help us find powers. Our powers are usually time because we're looking at like the time car depreciation, the time we gain interest, the time of like an Ebola outbreak. And those times are in the power position. So how do we solve for those powers? The answer is logarithms. All right. So what does a logarithm tell us? It tells us a power. So this is going to get into that first part of the lesson now. So it's super important. Logarithm is an exponent. So if I write something like 10 to the third power equals 1,000, another way to write that is 3 equals log base 10 of 1,000. And this just says 3 is, 3 is the power of 10 to get 1,000. Or 1,000 is the third power of 10. You can view it in a couple of different ways there. So if I see something like log of 1,000, and I know, right, if I just think about 1,000 for a minute, that it's 10 to the third power, right? What power of 10 makes 1,000? Well, the answer is 3. So if somebody says, okay, what would be the log of 10 to the fifth? What power of 10 gives you 10 to the fifth? Well, it would be 5, because a logarithm tells us what is the power. If there's no base written, we assume it's base 10. Let's take a look at the lesson. So in the lesson, they just want me to repeat that idea. So they want me to do it in 2 different ways. Let's blow this up. Try it again, blow it up. There we go. 1,000 is the third power of 10. A logarithm tells us what the power is. So the answer should be 3. If we're unsure, we can always ask our calculator. So on my calculator, new line, if I type log and 1,000, it's going to say 3 is the power of 10 to get 1,000, right? Log tells us, it just reports back. Give me a number, I'll tell you the power of 10. 100 is what power of 10? Why, it's the second power of 10. So the log of 10 raised to the second power has to be 2. 10 is what power of 10? Well, a number to the first power is itself, so I think that should be 1, because 10 is the same as 10 raised to the first. All right, now here's where things get interesting. So I want to break off for a sec here. Back to my notes. Oops, I don't want to do a screen share. I want to see my notes. There we go. Powers of 10, powers of anything, we'll do it in a couple of different ways. We know 10 cubed is 1,000. We know 10 squared is 100. We know 10 to the first is really 10. We talked about this one before. 10 to the power 0 is 1. Now, there's 2 patterns happening on my screen here. On the right side here, as I move down each step, you could say I'm dividing by 10 to get from one row to the next. On this side, I have a slightly different pattern. On this side, I'm going 3, 2, 1. I'm dropping the power by 1. So if I go 3, 2, 1, 0, what's the next obvious power? And my hope is you'll think -1. What is 10 to the -1 equal to? Well, if I continue that pattern on the other side of dividing by 10 again, then I get 1 divided by 10, 1/10. If I were to divide that by 10 again, then I'm going to get 1/100th. And if I drop that power by 1 again, I'm going to get 10 to the -2. So important things about these negative exponents right here, 2 things happen. First, a negative exponent does not give you a negative number. Super important. Negative exponents, what they really do is they flip the base. So instead of having a base of 10, my base is now 1/10. Now, if it's just a 1, there's nothing else to do. That's 1 over 10 to the 1, which is just 1 over 10, kind of boring. But with this one right here, with 10 to the -2, I basically have 2 instructions. The negative says flip it, and the 2 says square it. So if I flip it, I get 1/10, but I still have to deal with the 2. That gives me 1/10 times 1/10, which is 1/100th. Okay, or I could think about it as 1 over 10 squared. That's going to give me the same answer. So we are going to have to deal with negative exponents. Negative exponents just mean flip the base. That's it. Same thing would work for any base. So consider a base of 2. 2 to the third is 8. 2 to the second is 4. 2 to the first is 2. 2 to the 0, well, anything to the 0 is 1. We learned about that last week. The pattern on this side to drop down is basically divide by 2 each time. So if from the 1 I were to divide by 2 again, I'm going to get a 1/2. The pattern on the other side is drop the power by 1, so the next obvious power is -1. So I get 2 to the -1 is 1/2, right? I'm flipping the base. What would 2 to the -2 be? That would be flip it and square it. So if I flip it and then square it, I get 1/4, which also fits that divide by 2 pattern. So negative exponents flip the base. All right, back here. 1 is 10 to the 0 power, working that backwards. And 10 to the 0 power, the power is 0. What are we answering here? Here we're saying, what is the log if the base is 10? The base is 10, but the power has to be 0 to get a 1. Here, 1 over 10 is the same as 10 to the -1. What power do we see there? We see the power -1. Log tells us what power. We can always double check on our calculator. Use your log button. Log of 0.1 is -1. 0.01, what does that mean? Well, let's think about that for a second. That's a tenths hundredths. This is the log of 1/100th. What power of 10 is 1/100th? We actually went over that back here. 1/100th here is 0.01, right? Tenths hundredths, 1/100th. 1/100th is 10 to the -2. What power of 10 gives you 1/100th? The answer is that power is -2. So here I would have 10 raised to the power -2. And here I would have a -2 is the power I need. Right? So here we're just trying to get used to what the heck does a logarithm mean? It tells us the power we need for a base to get a certain result. So 3 is the power of 10 to get 1,000. 2 is the power of 10 to get 100. A logarithm is a power. It is the exponent. All right, important thing number 1. All right, so then there's some others for you to evaluate. I'm going to leave that part to you. Some tips on using a graphing calculator in a video. And again, I just showed you the Desmos one. Sometimes I use the Google calculator. And there's a log button right here. So if I say, hey, what's the log of 0.01 1/100th? I just learned that -2 is the power. That gives me 1/100th to the base 10. If I hit equals, it should say -2. So again, we're getting used to log on the calculator. Type this into your calculator, see what you get. Tell me 3 decimal places. And then how to use them to solve equations. So I'm going to do my question number 4. Yours is going to be similar. 3 times 10 to the power x equals 6,000. Let's see what we can do with that. So we have 3 times 10 to the power x equals 6,000. Now, if this was just like 10x or 10 plus x or something, bottom line, since the 3 is outside of the parentheses multiplied there, I'd have to divide to get rid of it. So the first thing I'm going to do is isolate where the variable is by getting rid of that 3. So I would divide by 3. And 3 goes into 6 twice. So 3 goes into 6,000 2,000 times. 3 over 3 is 1. 1 times 10 is 10. But I still have that to the x there. And that's equal to 2,000. So one way to do this is just to think about the logs the way I told you to, is that a log is an exponent. So when I look at this, I see the exponent is the log. The log has to have the same base as that. And then what's my target number? That goes in the parentheses here. And on a calculator, that would just be log 2000, because log assumes the base is 10. Another way to think about this is just like I can divide both sides by 3, I could actually apply the log to both sides of this. So this is kind of an alternate approach. I can write this as log base 10 of x has to equal log base 10 of 2000. And what does the log tell us about something? It tells us the power. What power do you see here? Well, I see x. Right, that's what the log reports back. It says, hey, what's the power? Oh, power's x. Done. That's that side. The other side has the log of 2000, which I came up with a slightly different way there. And bottom line is now I need a calculator. Can you do logs without a calculator? The answer is not easily. We ain't going there. So if I check back here, I want to know what the log of 2000 is. And I get 3.301 blah, blah, blah. How many decimal places did we want? We were asked 3 decimal places. So I'm going to test. If I plug in that number here, 3 times 10 to the x, I should get about 10,000. So let's see what does most things. So if I take 3 times 10 raised to the power, and I'm going to enter 3 decimal places, so 3.301, I get $5,999.59. That is close to 6,000, right? 6,000 was my target. If you want to get closer, throw on more decimal places. But here I was only asked for 3 decimal places. Do I get close to 6,000? Yep, that's pretty close. Just a few cents off out of 6,000. A few cents out of 6,000 is no big whoop. So I would report back 3.301. So we're just trying to get used to this idea of, to find a power, the only way to do that is to use a logarithm. So we have to isolate the exponent part, then apply our logarithm. Sometimes that's pretty straightforward. This one wasn't too bad. Sometimes it's a bit more work. Let's try another. All right, now this property of logarithms, I kind of showed it on the previous page of notes, but I didn't really say it. So now I'm just going to be a little more explicit about it. So this idea that the logarithm reports back the power, right? The power pops out. Now, if the power pops out, what was left behind? So I had written log of 10 to the power x. The formula on that previous screen said that should be equal to x times the log of 10. Right? The power just pops out as a multiple. Power was there, now it's out front as a times. What's this log of 10 still hanging out there? All right, well, let's think about that. We actually already answered this question on question number 1. Log of 10 is equal to what? Well, this says what power would you raise 10 to get 10? Well, I would raise it to the first power. So this log of 10 there is just a 1. 1 times x is x. Okay, there's other ways we can look at that too. Check this out. Suppose I had the log of 2 to the third power. Now, the rule we just had says that should be the same thing as 3 times the log of 2. Now, I don't know what the log of 2 is. I'd have to ask my calculator about that. But that rule says these two things should be the same number, whatever that number is. Let's check it on a calculator. So the first thing I had was log of 2 raised to the third power. And my wrong parentheses. My calculator says that's about 0.9-ish. My claim is that's the same thing as 3, pull the power out, times log of that base 2. Calculator says, yep, they're the same number for as many decimal places as I know. And this is another way I can go about solving equations. So let's test it out. First, they want us to just use this to rewrite, and it's very simple. The power just pops out. So all we want to do is rewrite it using that rule. So according to that rule, the first one for me should be x times the log of 1.03, and I can either type the word log or there's a log button here. Either one works. Uh-oh, hang on, cat fight in my house. So that would be my answer to the first one. Second one, the power is a bit more complicated, but the whole thing pops out. So for me, the 5x would pop out. And I would be left with that times the log of just 3. Oops, 3. And when you start a parentheses, close the parentheses. That's important. Here's a demonstration of solving. We're going to do that together, which is like what we did in the last problem, just slightly bigger numbers. So let's see, 40 times 3 to the x equals 6,000. Forty times, is it 3 to the x equals 6,000? Double check. Yep, that was my version, 3 decimal places. So like before, we want to isolate the x. We're going to get rid of the things outside first, so dividing by 40. Oops, different color maybe. On the left, 40 divided by 40 is 1. 1 times 3x is 3x. 3 to the x, excuse me, big difference. Here, I can divide top and bottom by 10. And then 4 does not completely go into 6, but 2 goes into 4 and 2 goes into 6. And then let's see, what do we have now? We have 300 over 2. Half of 300 is 150. That's not bad. So this says what power of 3 is 150? And the rule I used before was we apply a log of both sides. So log parentheses, the left side equals log parentheses, the right side. And then the next trick is that new rule, the power pops out. So we get x times the log of 3 equals the log of 150. Now, the log of 3, according to my calculator, is just some number that's being multiplied here. To get rid of it, I have to divide by that number. The log and the 3 are inseparable. Notice, although the power jumps out, we are stuck with that base in there. So I have to do that on the other side. Log of 3. You might be tempted to cross those logs out. That doesn't work. We'll see that on a calculator in a second. So on the left side here, I have a number divided by itself, which is 1. 1 times x is x. X is that crazy fraction right there. And then we'll test it on the original equation. See what happens. Calculator. Log of 150. And again, that log button, you can either type it if you're on a computer or pull it from the function menu here. And then divide by the log of 3. Now I get 4.56, blah, blah, blah. If I could just cancel the logs and say it's 150 over 3, I'm going to get a very different answer. Watch this, 150 over 3. 50 is nowhere near 4.5, which is the right answer. Well, I'll show you. I'm going to get rid of this because that ain't the right answer. This was going to solve the equation 40 times 3 to some power equals 6,000. My claim is the power is 4.5609 if I went to 4 decimal places. 4.5609. So I'm rounding up. That'll take me a little over 6,000. But notice I'm getting 6,000. If I tried to put 50 in there instead, check this out. Whoa, 2 blah, blah, blah times 10 to the 25th. So that means move the decimal place 25 times to the right, and we get some number I don't even know how to name. All right, that ain't right. Logs don't cancel like that in division. You're stuck with them. Super important. So maybe to 3 decimal places, it would be 4.561 for my version of this problem. All right, so I solved it and checked it. Checking by going back to the original expression, plugging in the number I thought I found. So then we're just going to apply this to some situations. So I'm just going to get these situations set up, and then I'll let you finish them. So let's grab both of these. Screenshot. And yours will be a little bit different. Different numbers, same process. So for number 7 here, I want to know, given this depreciation formula right here, so if that's 0.82, that's 82%. So that means my car must be losing 18% per year. 100 minus 18 is 82%. Determine when the value of the car will be 12,000. So I would try to solve the equation. 18,000 times 0.82 to the power t. I want to know, when does that equal 12,000? So same set of steps we applied before, we're going to divide, and then we're going to apply logarithms to solve it. So I would divide by the 18,000, divide by the 18,000. That's going to leave 0.82 to the power t. And do you have to reduce this? The answer is no, but I can see I could divide top and bottom by 1,000. And then let's see, 6 goes into 12 twice, into 18 3 times. So if you see it reduces it, but it's not a big deal if you don't. I'm not going to put that in as a decimal because then I'll have to round and round again. Then the next trick is we use the log on both sides. So log of 0.82t, just like before, different base, equals log of, in this case, I have 2/3 there. The t pops out of the log. So I get t times that log. To get rid of the multiplication, we're going to divide that log to the other side. So in the numerator, I have the log of 2/3, parentheses are necessary. In the denominator, I have the log of 0.82. So the next thing I would do is plug this fraction into my calculator. And then I would check it by plugging that number back in here to see if I get 12,000. So for the next one, I'm going to set it up, but let you solve it. So the population of a town was 72,000 in 2010 and is growing by 8% each year. Okay, so that's a relative growth rate. It's relative change. Relative change is percent change. When will the population reach 160,000 if this trend continues? So they want to know how many years after 2010. Okay, so we'll let t be years after 2010. Oops, numbers, digits in the wrong order. That's better. If 8% is the growth rate, then 1 plus 8% as a decimal is my growth multiplier, 1.08. Right? That's what we call the multiplier. Now notice I'm starting with 72,000, I'm ending with 160,000. So I'm just going to ignore the thousands and say my formula for the population is 72 times that 1.08 to the power t years after 2010. And I want to know when that is equal to 160. So then it's kind of the same procedure we did up here. We're going to divide by 72. We're We're going to apply the log, we're going to divide, and we'll have an answer. So I'm going to let you try to finish this using the steps we used in the last couple of problems.